Yeah, intro music, baby. It's here. That was fun. How's it going? I am excited for today. I got a lot going on over here. I couldn't sleep. I've actually been up since 3 in the morning messing with this. So I was up kind of just messing with it all day yesterday too. Uh, this this is just incredibly cool. I gotta go over what we're doing here because this is I don't think uh, tooling like this exists anywhere. And it's hold on just a second. Let's start this little guy up again. It's the tooling that I originally wrote from the last pickle, and I've since forked and rebranded, and I am using it. Actually, hold on. I'm gonna stand up today. This is a big day. High energy. All right. There we go. Okay, everyone. So, what are we doing today? I am taking a look at a build of Cassandra 5 that was as of last night. I'm going to show you how I do that, and I'm going to show you a little bit about the stress tool that I'm using to run this, and we're going to take a look at the cluster that I have running right now. That's sitting here, and I'm just hitting it with requests while we're talking right now, and doing all sorts of interesting analysis on it. I also have a follow-up from last week. I'm actually going to start with follow-up from last week that is pretty exciting. So let's just jump in. Let's just jump in here. So this is something that I had. Hey, what's up, Sarma? How you doing, buddy? Welcome back, man. Hope you're excited for today, pal. We've got oh yeah, there we go. So we've got last week I took a look at EBS efficiency, and I can drop a link in the description later on, or I don't know if someone has it handy and can drop that. But basically, what I was taking a look at is how efficient is it to do sequential I/O, just in general on an EBS volume. And the stuff when I say EBS, I'm actually really referring to any disaggregated storage across, to my knowledge, every cloud provider. So if you're going to look at Azure, this is a problem. This is going to affect you there. But the thing is, this actually affects everything. So even if you have like NVMe or floppy drives, whatever, like every single type of storage has some is going to be impacted. So basically the test was, what happens if we do super tiny reads off of an EBS volume, or if we're doing larger reads. And I actually broke something out, and it did multiple sequential tests that went larger and larger and larger. And basically what AWS has in their documentation, and I was able to verify this, is that when you say, like, if you want a GP3 volume, if you say that you want 3,000 IOPS, because that's the testing that I did, every time you do a request to that drive, if you're blocking on it, if you do multiple requests, and it can actually send them together, and you can get your responses together, and it won't really count as two. But if I send, let's say, a request for 4K off my desk, right, and then another one for 4K, and then another one, and then another one. Okay, I've asked for 16K. The problem is that counts as 4 IOPS. If I ask for 16K in a single request, then that counts as one ion. Okay. So basically, the thing that the reason why I care about this is because if we take a look at the way Cassandra behaves when it's reading SS tables during compaction, we're actually reading only a chunk at a time. By a chunk, I mean a compressed block. So um, when you look at a Cassandra schema, let me just pull this up now because this is starting to. I'm going to get in the weeds here early, and you know, if you've watched me before, you know that I can't help it. I get in the weeds too fast. I love the tech. So this is a table right here, right? So right now we're just using size tiered compaction strategy. Actually, I turned on a stress job and never changed it. So what we're going to do is do the alter on here. But anyway, but what you'll see is regarding when I was talking about chunks, you'll see this compression. Oops. All right. Hopefully this is legible. Someone's going to have to tell me. Maybe that. We're going crazy big font. So compression chunk length in KB equals 16. Okay. So I've explained this in a few times, but I think it's worth repeating. The chunk is the size. The chunk length is the size of Cassandra's internal buffer that gets filled up with data when compaction or just in an SS table. So if you're writing out an SS table and it's compressed, what happens is you first write it into that buffer, or Cassandra writes it into that buffer, compresses it, and then writes it out to disk with some metadata. The problem here is that if we have, well, let me take a step back. Not the problem here. With a lot of workloads, like if you're running lightweight transactions or counters, or you just have small reads, it's a really good idea to use a smaller chunk length. And the reason for that is because when you go to read your data off disk, if you use a smaller chunk length, then you're going to have to read less data off disk, which means you have to spend less time doing decompression because it's a smaller amount of data, and you're not reading as much off disk. So like the thing is, disks have limited throughput available to them. You have a limited bandwidth. And so if every request that you do like reads, I mean, in Cassandra before 4.0, it would be a 64K chunk length by default. So you'd be reading, and again, let's suppose you get a 50% compression ratio, you're reading 32K off disk, and maybe you only need 100 bytes or something like that. So the read amplification is crazy here because you put extra pressure on your disk, and you put extra pressure on your CPU, and you put extra pressure on the GVM. It's basically just all around terrible. So you don't want to do that. So in Cassandra 4, we made the change to go to a 16 KB chunk length. So for those types of workloads, but out of the box, you're actually going to get about 4 times improvement in efficiency on your disks for those type of workloads. And if you are running lightweight transactions and counters, my advice to you is to figure out how, like, what the size of the data is that you're actually going to be doing lightweight transactions with, and use a chunk length that's small, that's really small. Typically, lightweight transactions are, you're updating like a value, like a really small value, like an email or an enum, and you're changing state of something, or you're changing an integer, right? So there's really not like, the best thing that you can do for lightweight transactions is to have the whatever data is involved in that lightweight transaction in a standalone table with the smallest chunk length possible, ideally 4K. And that way you get the best throughput and the lowest latency on your reads. The problem here is when you decide that you need to stream or read a lot of data. So if you want to stream out an entire table that's using a really tiny chunk length, the problem is that Cassandra only reads a tiny chunk at a time. So if you're compressed from 4K to 2K, 50%, Cassandra is going to try and stream 2K worth of data at a time, and it's going to block in between every single operation. So if we're using EBS, and we know that one IOP, like it's going to count as one IOP, no matter if we read that 2K or if we read 4, 8, 16, etc., all the way up to 256. It's in our best interest to read 256K at a time. In fact, from a throughput perspective, it's always better to read those larger values because you don't want to spend as much time waiting on IO. Like if you do 100 IO operations, it's going to take longer than if you do one. That's just basic math. And in this case, so if you go from 4K to 256, that's 64. So you're going to spend a little bit more time on each request, but every single request that you do is going to carry with it some overhead. And so the best thing that we can do is to start performing larger reads during streaming operations and compaction operations. So that's what this JIRA is about. So if you're interested in learning a little bit about what's going on here, and I'm just going to go ahead and make this a little bit bigger, improve. So if you want to learn about this, look for Cassandra 5.0. It's improve disk access patterns during compaction and streaming. So what we have here is three things that should reduce the amount of overhead on your system during compaction and streaming. It should allow them to be a lot faster. And maybe most importantly, it's actually going to help you reduce your costs. So the reason why this matters so much, if you don't massively over provision on your EBS volumes, then what happens is when you go to bootstrap a new node into the cluster, you're only going to be reading that 2K at a time, and that I just mentioned. And so instead of reading 256K, you're going to be reading like 2. And in this case, that's 128x difference in IOPS. So for every single like 200, so you could either do one IOP and stream 256K, or you can do 128 IOPS and read 2K at a time. So this, what happens is that when you're reading those small values, you hit your IOPS limit and AWS cuts you off. And so I actually posted these numbers. These are really interesting. So this is what we have here. Can you see this? Oops. So if you look here, just looking at 4K request size, our throughput is limited to 11.9 megs a second. Okay. If we are going to read 256K, then our throughput goes all the way up to 128 megs a second. Right. So this is a 10x difference in performance. So basically what I'm trying to do here is optimize the way that we talk to our hardware so that when we do things like streaming, we can read big chunks of data. And when we do things like lightweight transactions, we only need to read a tiny amount, because that way we have each use case is optimized for it, rather than relying on read ahead, which introduces additional latency and artificially pushes up your throughput, and then you're more likely to actually reach the throughput limit of the device. So basically, this is kind of a hope here. So I've talked about some of these tools before. XFS slower. What we have here kind of is this is the table that has 4K chunk length, and we're doing compaction. And you can see here that this is reading 4096, 4096, 3763. These reads are super small, and this is happening all the time because it's during the compaction process. So basically, what we have now, the problem that we have now is, and this is probably one of the biggest obstacles to running EBS at scale in a cost-effective manner. Cassandra is using the disks inefficiently. And so what we can do is read everything into a do larger reads into a buffer, and then basically pull from that buffer within the JVM. So it does two things. One, reduces the number of total IOPS that we use on the system. Two, it improves our overall throughput. And three, it reduces the number of system calls that we're doing to our OS. So those are all good things. So if we can get this in, I'm really, really hoping we can get this into Cassandra 5. Worst case is Cassandra 5.1. It might require a little bit of work because there's a whole bunch of internals. And I am working with Jordan West on this. Jordan is also a Cassandra committer, works at Netflix, and we've worked together both. We both worked at Apple. We both worked at Netflix. We fixed a bunch of production issues together. I'm really hoping that I can have him talk about this with me, because he's actually reading a lot of the code and going in there. I'm more of I figure out what's going on, and I know all the Linux utilities. Yeah. So anyway, the dream here is collaboration between multiple people in order to try and get a big efficiency gain. And if we can get this in, then maybe we can even look at backporting it, because this is going to be so useful that it will actually reduce. It can make a massive difference in the overall cost to run a Cassandra cluster, because Cassandra clusters are largely, the cost is largely dominated by one, if you're on EBS, it's going to be largely dominated by how long it takes to add new nodes. That's going to be a big part of it. And two, whether or not you what settings you have to use on these provision volumes. So if you're using GP3 and you have to pick between 20,000 IOPS or 5,000 IOPS, well, that's going to be a big cost difference, because you pay for IOPS, and it's just kind of crazy. So, and the reason why it affects cost is because the amount of data that you can fit on each node is related to time to repair, the time to compact, and time to replace nodes, and time to bootstrap new nodes. If it takes you 2 weeks to bootstrap a new node into production, you're going to want to put more nodes in your cluster. That's a big part of the reason why there's so much advice out there when people say use 500 gigs of data per node. The problem isn't inherently that there's no technical limitation that is present that isn't something that we can overcome. We can actually make it so that compaction runs a lot more efficiently. We can make it so that repairs run more efficiently, as well as streaming, so bootstrapping. So this is a big deal. So that's a really, really long winded answer, but if you're interested in what's going on here, take a look. Like I said, it's Cassandra 15.4.5.2. I'm really excited at the idea of solving this problem, because this is gonna this will help a lot of people. Okay, so on to what we're doing this week. This week I'm taking a look at UCS. UCS is really, really interesting. If you haven't taken a look at it yet, I really recommend reading this blog post. This blog is probably the best. It's actually the best source of information, and so because it's an easy read. The documentation for UCS is pretty long. It's 30 pages long and includes a lot of details. And honestly, it's you have to be really committed to read it, because it's very, very deep in technical details. It's got a lot there, and if all that you want to do is turn it on, it doesn't really help you. So I would read this, because this is great. Wow, a lot. All right, let's take a look at some stuff. So I have set up an environment, and this environment I've built with my tool, EasyCastLab. EasyCastLab is, I think it's pretty cool. It allows you to, in just a few lines of shell, provision a Cassandra cluster running really anything that you want. I can show you just what I mean by that. I mean, I realize that's kind of like probably sounds like a totally insane statement, anything that you want, but it actually is possible to run anything you want. So let's just resize this a little bit. Okay. So what do I mean by whatever you want? Obviously, like, you know, we're not going to run Mongo on here. But what we have here is a command line tool that lets you launch clusters. And so if we go to, so if we take a look now, I actually have a cluster up and running already. And I'll just show you what that looks like in just a sec. But, you know, I asked it for, I asked it to give me i3x large, which you can see these are just some notes I made. We have on here, we have 30 gigs of RAM, 4 CPUs, and a 950 gig NVMe drive. So nice and fast on the storage side. Not a lot of horsepower on the CPU side. To be honest, I'm a little, you know, I need to go back and test 5.0 versus 4.0 and see where we're at. This is kind of just kick the tires right now. So we'll see what the performance looks like. I've also put in like a whole bunch of settings that, you know, I haven't tested and really verified. This really is what you're seeing right now is me evaluating this for the first time. And this is also like literally, like I said, this build was built yesterday. So let's see. So this command right here, EasyCastLab init S1C3. This says give me 1 stress instance and 3 Cassandra instances. You say CastLab up. And then you say use 5.0 head. What does that mean? Well, EasyCastLab works with Packer, and Packer builds AMIs. And so I have this process that builds let me just open this up, an AMI that supports multiple versions of Cassandra, multiple versions of Java, and multiple versions of Python. And so basically what we can do here is specify that like this is version 3.0. It's located here. It uses Java 8, Python 2.7, and the Java config to change things is JVM options. I'll tell you about that in just a minute. You can see here's 4.0, that's Java 11, 5.0 beta 1. So if you wanted to use the first beta that came out, you can do that. And that's cool here. But here's the thing this is where things get really interesting and in my opinion, really powerful. So this, I just said, this is version trunk, but instead of putting a URL to a tarball, I'm actually putting a link to a Git repo and I'm specifying a branch. And what actually happens during the build process is it checks this repo out, does the build, and puts it in under the name trunk. We then also say that I want to do 5.0 head, and it pulls the Cassandra repo, and you can specify a branch. So the reason why this is cool is because you can add an arbitrary, like if you have a Cassandra build, let's say you want to test something, you can go ahead and make a change. You can add a new block in here. You can add something right here, for example, and you can then do your own build of Cassandra. And when you run the Packer image, when you run Packer build Cassandra .packer.hcl or whatever the command is, when you run that, it will build your Cassandra image for you, and it will include all of these versions. So when I go over here, I can do this, EasyCastLab ls, and it will actually tell me all of the images. This executed, you can see here, it says executed remote command. This hops on the image and gets all of the remote builds that are on the machine. So there's just this directory here. So I'll just show you real quick. So if I So if I do this, and now I'm on the Sheen, and you get this this environment file that gives you a bunch of aliases. This is actually the same tooling that we're going to be using in my training course. So if you look at this and you say like, oh, this is really cool, this is interesting, I want to like learn more about this. My training course starts in just a few weeks, actually, like 4 weeks from yesterday. There's going to be you will be able to learn a ton about how to understand how Cassandra works. And this is for people that are already operators. So we go here, we can say user, let me do it this way. So user local Cassandra. This has all the Cassandra versions, 3.0, 3.1, 4.11, sorry, 4.1, 4.0, 4.1, 5.0 head, 5.01, sorry, 5.0 beta 1, trunk. And then we have something here that's called current. Current is a hard link. Current is a soft link. And the soft link is when you do like use 4.1, that goes in and basically mucks with the server, changes the Java version for you, changes the Python version for you, and relinks Cassandra. On the server itself, one thing that's kind of cool is that all the data is, all the data is located in Mount Cassandra data. And so you actually have the ability to test upgrades. You have the ability to test mixed version clusters. You can do some wild stuff with this. And then one of the last things I'm gonna touch on before I get going here into the actual cluster to mess around with it. We have the ability to modify the JVM options and the Cassandra YAML. And it's actually really easy. So when you say use 3.0 or whatever it is, one of the things it's going to do is drop a couple files locally for you. So when you do use, let's say 3.0 or 5.0 head, the first thing it does is it generates a local Cassandra patch file. The local Cassandra patch files are fragments of the Cassandra YAML. You don't need the whole Cassandra YAML. In fact, when I was designing this, I found it was kind of a lot for you to need to worry about the original Cassandra YAML. What you can do instead is in here. So what this generates, this cassandra.patch.yaml, is it gives you a cluster. It sets num tokens to 4. You can change this. You don't have to use this. It automatically sets the seed provider for you. So it puts the hosts in the seed provider. It sets up your different directories, and it gives you the EC2 snitch because you're on Amazon. Okay, so what we want is the ability to have 30 node clusters, and this will automatically use the EC2 snitch so that your data isn't like all weird and distributed all over the place. So we also like here we have the ability to set like the SS table format. I went ahead and put compaction through the roof because I'm curious what this is going to look like. Stream SS table, entire SS tables true. If I have enough time after this, I'm going to go ahead and I may do a test where I rebuild a node and see what happens when we stream other stuff into it. And then these limits. So these limits are low on the by default because that's probably safe, and because this is a sandbox environment and I don't care about safety, I'm actually deliberately going to be breaking stuff here. I love breaking stuff. It's when I break things that I realize how they work. So yeah, so this is the environment. Then there's a command called upload config. So it's if we look here, easy cast lab update config. Sorry. So what this does is updates the Cassandra YAML, and I need to update the note here, and it also updates the JMX config. So the JVM options. JVM options, this just pulls down the original thing. It turns out that There are some options that are exclusive to like G1 or ZGC or Parnu and CMS. And so it ends up being kind of a headache to try and think like, okay, which GC algorithm am I using? Let's go ahead and like pull out the settings that it doesn't need. I don't want to deal with that. So what I've done here is for this, we're on Java 17. I'm going and using ZGC, and this is using 16 gigs of heap. So I think that this is kind of a cool test, because we're not only using ZGC, but you can look here and you can see what's changed. We're also using the new storage engine format, and we're using crazy high, like maybe not crazy high, but pretty high values for compaction throughput and these options here. So yeah, I guess I'm just gonna jump in and let's take a look at the environment. So here is a stress node right now, and it is running about 15,000. It's configured to run 15,000 operations per second. And it's been running for a little while now. It looks like we're in the, it just hit 24 million, 24 million queries. And I just started this like right before the stream started. You'd have to do the math and tell me, you can tell me when I started it. Let's make this bigger. Hopefully that's visible. I'm just going to make more tabs here because it's going to be a lot easier. Okay. Okay. Talking databases. This tool is MP-Stat. MP-Stat is a really nice, it basically gives you like a multi-processor statistics tool. If you do -p all and then 1 every second, it's going to give you an update as to what's going on in the system. So in aggregate, this is reporting that we are, look at that, 65% idle. So, you know, this is doing fine. Our write latency is hovering around 4 to 6 milliseconds. Our read latency is around 7.6. And the workload that we're running here is the random access workload. The reason why I'm doing the random access workload, and I'll just stop it for a second, I'll show you what that is. So this random partition access, what this does is it creates a wide partition, and you can adjust the number of values that you want in there. So this says workload.rows equals 100,000. And then over here, it says r-r.1. That means 10% of our queries are going to be reads. And rate, that's just 15,000 queries per second. -d is 5 hours. And then -p, 10m, that's 10 million partitions. So the reason why I've been running this off and on in the morning is because I was trying to get a lot of data. I was trying to get a bunch of data in here. So just going to go ahead and start that back up again. You can see here, it doesn't by default drop your tables. So we're actually just picking back up where we left off. Let's see. Okay, so back here, we can see that, oops. Okay, so about 90% idle right now. Let's see how we do. Let's see how we're doing with compaction. So I'm just gonna leave this here. I'm gonna set up, let's see. Where are we going to do this? Let's go here. So let's hop on a new node, and then we will run. Oops. We're just going to hop on. We'll jump into CQLSH. And what I'm going to do is I'm going to do something else first, actually. I'm curious. Should have looked at this. So node tool. Compaction stats. Okay. All right. So this is not behind at all with compaction. We actually have, I kind of wanted to put this under a little bit more pressure. So what I'm going to do here is I'm going to stop my stress program, and I am going to increase this to 20K requests a second. I'm not going to get into this now, but there is a mode in EasyCast Stress where you can tell it what your latency, what your target latency is, and it will try and find it. I am seeing some odd fluctuations on the server, so I'm trying to get some consistent numbers, and I actually want to break it. So I'm just going to go ahead and use the rate limit. I think that 20,000 will end up breaking it. It does seem to, the latency numbers do end up jumping up a little bit. And one thing to keep in mind is that the first number is always going to be higher, and then it drops. There's a new algorithm in here to prevent these numbers from being like wildly wrong. There's this, it basically steps up the number of requests as it does a warm-up phase. Pretty fun. So we can go here and we see that we are at 76%, and I'm actually a little bit surprised that we only saw compactions completed was surprisingly low. I suppose that's probably because by default, we're only getting 4 gig. We have 4 gig mem tables. And the reason why I have 4 gig mem tables is I've allowed Cassandra to set that automatically. I didn't set that over here. So the result of having really large mem tables is that they just don't flush as often. And as a result, we're only seeing 30 compactions here. So maybe what I'm going to do is I'm going to stop this again. I'm going to go ahead and we're just going to turn this, we're going to turn up the writes on here. And we are going to just say, like, let's go ahead and do 25,000 queries per second. So this is only a 3-node cluster. Like I said, this is not particularly large on the size. i3XL, 30 gigs of RAM, 4 CPUs. So I'm just trying to find a spot where these numbers sort of, the CPU starts to get a little bit stressed. The thing is, when you have NVMe drives, your storage is never really your bottleneck. Your bottleneck with Cassandra and an NVMe drive, unless it's been configured totally wrong, is going to be your CPU. It's always your CPU. So let's see. So, okay, so we're ramping up these writes. You can see the write latency occasionally will spike up. Be good to know why that's going on. Here we go, 8,000 write latency is coming down. So these numbers, you can see they're getting stepped up, and we are moving along. So we're at 10,000. See, these write latencies are picking up. So let's see what is going on here. 55% idle. That's not what we want to see. So look at this. So now we're at 13,000, and this guy is over here with 200 write latency of 200 milliseconds P99. Now, one thing that's really interesting is when we look at proxy histograms, we actually can see, let's see. So here's what's interesting. This is only reporting that our P99 is 1.5 milliseconds. But when we look over here, we see that this number is really high. So it's a really good idea to try to figure out like what's going on there. So the question is, did I do something in my tooling? Totally possible. I may not have done maybe I broke something, or maybe there's some queuing going on, or maybe there's something happening in the driver. Let's just take a quick look at that. So open up another window. Let's see. Go on the lab. So when you'll see me do this a lot, whenever you're in the directory that you used to set up the cluster, it uses that kind of as like a working directory. You do not want to commit those files and post them anywhere. I have an open bug. If you do that, you will accidentally be sharing your AWS key. Don't do that. but I do have some aliases here that make some things a little bit easier. So I can do like stress 0. And this knows exactly where stress 0 is. It doesn't mess with your host. It doesn't mess with anything. It's all in this environment thing. So let's see. So here we're going to do, we'll let it go by default. So if I grab this, I can now use a tool called ASProp. ASProp is awesome. So ASProp, we're going to just say, give me my output. We're going to put it in the temp directory, and we're just going to say this is from stress on screen.html, and we will go ahead and pass the ID or the PID. So this is going to go ahead and profile. So we'll find out what's going on over here, because this is a little bit higher than I wanted to see, especially since these numbers are not totally maxed out. Don't know what's going on. Okay. What else are we going to take a look at? I mentioned ZGC. So if you are trying to figure out, or if you're curious about if Cassandra's performance with ZGC is any good, you're going to want to use Java 17 because it just is more mature. There's been some improvements in the latest builds of Java, and here we can actually take a look at the metrics. So this is pretty good. This is a 1 millisecond pause. So you're actually going to see these numbers expressed in nanoseconds. Occasionally, we'll see some stuff like this. This just means that we have the rate of allocation is faster than the rate of cleanup. So ZGC will actually work better with bigger heaps because if you think about the rate of allocation in Cassandra as being more or less constant, as it fills up the heap, bigger heaps take longer to fill, so there's more time to clean. So bigger heaps are good. But this is only a 16 gig heap. I was a little nervous. Here we can see that this is a pretty good pause here. So yeah, not bad. 2 milliseconds. Okay, so we're not seeing long GC pauses. ZGC is actually looking really good, and if we continue to make improvements into the allocation rate of Cassandra, we should be at a point where like Java 17, Java 21, you just don't see long GC pauses anymore. So hopefully we get some more of those improvements in, because this is a pretty big deal. Just seeing these numbers are like really exciting. And I don't know if anyone saw there was a video that we talked about what we were really excited about Cassandra 5. I said Java 17 because the only parameters that you have to use to set this, if you notice, I commented a whole bunch of stuff out here. This is it. Use ZGC and then its size, and you're done. And it just goes. And you can see I'm getting like really, really good pause times. 3 milliseconds. Who cares? All right. And then here, so this is actually, see this reallocation stall? This is probably what the problem is, because we're seeing these reallocation stalls. So I need to double check what an allocation and a reallocation stall is, but if this is a blocking operation, then when this stuff comes through, that might explain things. I need to check though. I haven't looked into that yet. Anyway, so what are we doing here now? This is running. This is getting pretty high latency. This is actually pretty bad. We're seeing a ton of errors over here. So this Did this correspond to the allocation errors that we're seeing over here? Maybe it did. I wish I had the timestamp field in here. That would have been smart. Okay, so what I'm going to do is I'm going to back this thing off because there's no reason to absolutely destroy my cluster right now because I actually want to do something useful here. We're going to let this thing chill out for a second. And let's just take a look. Okay, so we're basically idle. We can just ramp it right back up. Okay, so this right here, alter table random access with compaction, because right now we're using size tier. So I'm just going to go ahead. I'm going to switch this over, and I'm going to use. I'm not going to use this exactly. So I'm going to. Where's my scratch? Here. So see this alter table. Okay, so there I'm using key value. What I'm going to do here is alter random access. And the interesting thing about this, whoops. So I'm going to take 2 seconds here. I'm going to stop this again. We can actually do this. So if we do, let's see, easy cast, whoops. Easy cast stress. I'm using a build that I did this morning of this that has some features that that I wanted that I wrote a few days ago. But let's suppose I wanted to do like I don't know. Let's go with counters wide. I don't know if this is what this is going to do here. So we're going to run counters wide. And the reason why it'll become clear why I'm showing this to you in just a moment. We're just going to say compaction, UCS, and then T4. Okay, so UCS has these interesting options. Like it can do leveled or it can do size tiered, but it does a better job of size tiered than size tiered because it won't like result in these massive SS tables. So I just wrote this, and I got to be honest, I've never run this command. This is literally new. Probably won't work. If it does, I'll be shocked. There it goes, totally broken. Run counters wide. Oh, boom. Okay. And I did not do it correctly, so that's on me. That's what happens when you demo stuff. This is how you know that I demo things live because my stuff is broken. So we're just going to go ahead and run this alter command. Let's see what happens. Alter. Taking a while. Why is it taking so long? There we go. And then we can describe, and now we see that we're using the unified compaction strategy. I don't know if that's going to result in a whole bunch of, you know, I don't know if a bunch of stuff is going to recompact. I'm not sure how this is even going to behave. So let's just take a look over here. This is probably should have grabbed that. Let's just grab that real quick. So this original thing, I know I'm bouncing around all over the place. This is just how my brain works. We're just going to FTP into stress 0. Oops. This probably won't work. Oh, there it goes. Cool. Open. Stress on stream. Boom. What do we get? CPU profile. Nice. So this is where my time is being spent. So I don't see anything in here that's like sticking out in a huge way. There's there could be like a lock or something preventing this from running, but I have a feeling that the issue is on the Cassandra side. I'll have to do more checking into this. Easy Cast Stress is also using the version 3 of the Cassandra driver, so I need to upgrade that. Anyway, back to where we were before. Lots of talking. No drinks, no water breaks. That's how I roll now. So we're just, let's see, idle. Nope. Run. Nice. All right. So this here, this does have a if not exists. So because these do exist, you can just not worry about it. So here, whoops. Man, it would be great if I could type node tool compaction stats. So let's see. So this is one of the things that's interesting about UCS. UCS, one of the things that it says is that it won't like aggressively recompact. Like if you switch between like leveled and size tiered, you can end up with like some compaction craziness. You won't get according to the documentation and the original in the paper. According to that, you won't get everything recompacting. I don't know how or why, but that's why we're here. I'm literally here to break this. So if I go to mount Cassandra data, easy, random. Okay, so what's it doing? Not even sure. So you can see I'm getting occasional error over here. So why is it erroring? That would be nice to know. So basically one of the things that you want to do when, like, if you're in a situation like this and you're saying, there's like occasionally errors happening over here, but I'm not really sure what's going on. There's a few things that you want to do. One, and I talk a little bit about this. I talk a lot about this in the training session starting next month. Shameless plug. One of the things that I really love that I got out of working at the last pickle is understanding something called the OODA loop. Now, this is sort of just how my brain works, right? Like, and so this really resonated with me. The idea is that we break up the task of problem solving into multiple phases. Observe, orient, decide, and act. Observe, that's where we're at right now. We're just looking at stuff. And here's the thing. Most of the teams I've worked with, and I mean, I've worked with hundreds of teams. When I was working at TLP, I was working with a different team almost every week. And I did that for years. Most teams will take a guess at what they think the thing that's broken is. So someone will go, was it GC? And then they look at the thing, and then they're like 2 minutes later, like, oh no, it's not GC. Okay. Is it disk, or is it compaction, or is it blah, right? The problem with that is that there's like hundreds of things that could be wrong. And when you just say like, is it blah? And then you try to check the symptoms to see if they match up with it being blah, you're literally just throwing darts at the wall. It's a complete waste of time. So not going to get into it now, but the whole idea is that what we want to do in order to understand what happens when things are going wrong, like this right here, for example, these errors that are coming up, like we're getting a ton of errors. I'm seeing 13,000, 14,000 requests per second and like a lot of errors. So there's something weird happening here, right? But we don't know what it is. We don't know if it's on the side of my stress tool. It could be easy cache stress. I don't know. It could be Cassandra. So right now, rather than saying like, is it GC? Is it whatever? We go into the observe phase, right? What observations can we make? Well, one, we want to understand what our system looks like. So this is a MP stat is really nice. The reason why I have it up here is because it's one of the first tools that I use, because it can give us a nice breakdown of what your CPU is doing. In this particular case, it looks like it's 66% idle. So I don't know what's going on there. why do we, oh, now we're stabilizing. So why did we have a ton of errors over here? Like, total mystery. And why were we getting 100 something a second? So we say, okay, were we running out of resources, right? We want to be resource focused first, because understanding your resources can tell you a lot about what the system is doing underneath. So, you know, what is our CPU usage? What does our IO look like? Here we can see there's actually not that much going on at this moment in time. In fact, it never really looks like there was a lot going on. So there, like I said, there's a chance that like this is just my fault. It could be something that I broke. So let's actually check on that. So what we'll do is we'll just check on the oops. So let's go ahead and we'll open up a new window, and so let's see. And by the way, let's just do node tool compaction stats. Cool. So these aren't even, oh, these are hardly doing anything. I know how we can get this to behave a little bit more crazy, which we will do in just a moment. So a little bit, let me just take a step back real quick. Unified compaction strategy has this thing called scaling parameters. Okay, scaling parameters affect the way that the data is tiered out on disk. Okay, so if you have a scaling parameter that starts with an L, that means it's going to behave like leveled. So that means there's a whole bunch of data in the level, and that gets compacted together, and then eventually it gets merged into the higher level. When you have size tiered, the way that it works is it takes SS tables that are similar in size and it compacts them together, and then you end up with bigger ones. The problem with size tiered is that you end up with really huge SS tables after a while. I've actually worked back when I was at TLP. I worked with a team that had SS tables that were they were close to a terabyte. So it was like they would just sit there. And the big problem with size tiered when it gets like that is when you have an SS table that sits there for a really long time, it can have tombstones in it that shadow other data, then the other data can't be dropped, or you can just end up with a whole bunch of like SS tables per read, which slow things down. It also makes backups kind of weird because now you have this like huge file that gets rewritten sometimes, and like you know, now you have to back up like a 1 terabyte SS table. Like it's just kind of ridiculous. So one of the nice advantages into UCS is that it will break up SS tables at predetermined boundaries. And so when you use your scaling parameters and you pass T4 or T8, T8 just means tiered 8. Tiered 8 is like size tiered compaction, but it waits for 8 SS tables of the same size to be grouped together. So basically, when you start doing T and you go higher and higher in the numbers, you end up with something that's more and more friendly for write-heavy workloads, because you're basically delaying compaction until you have 8 tables that are, you know, similar in size that can be compacted together. So I think, based on what I've seen so far and I've read, my understanding of this, if you have a write-heavy workload, and the reason why I picked random access is because it's not a time series workload. It's actually just accesses random rows within the partition. The reason why I like this is because if you have a write-heavy workload that does do that type of random access, and it isn't going to work well with TWCS, then UCS with a higher T value should allow you to run those workloads, because again, you're going to have low levels of read and write amplification. So let's see. Oops. So if we look here in the documentation, you can see that this is here, right? So basically, it's really, really, really smart design that does a whole bunch of, like, what I like about it is it's a nuanced, intelligent design that fixes subtle issues that cause each compaction strategy to have like some flaws. So for write-heavy workloads where leveled compaction is not going to be a good fit because of the amount of read and write amplification, UCS looks like it is a no-brainer replacement. Even if you use T4, which is the same setting as size tier by default. We can verify that by going into CQL-SH. Waiting for CQL-SH. Oh. Okay, so it is timing out. So I was doing a little bit of a thing, and then I broke away from it to explain something and mess around. And now all of a sudden I'm seeing timeouts. So I need to figure out why there's timeouts going on over here. That's interesting that there's timeouts. Okay, kicking the tires. This is why it's not released yet. We are figuring this out. So if we go to use, and then by default, any workloads that you run in EasyCast stress are going to be in the EasyCast stress key space. We're going to say access, random access, unified, right? But if we look at, let's say we just do key value with compaction. Come on. Let's say we don't even apply any parameters, so we just leave it. This might actually cause it to start behaving really weird. And see, this is kind of one of those things with the observation. I'm seeing timeouts here, right? But we're 63% idle. We shouldn't be seeing timeouts. So I need to figure out why we would be seeing timeouts when we're 63% idle. Anyway, and this is why we have this environment. So the reason why I love this tooling and the environments that it creates is because I can safely break stuff and be like, how do I learn how to fix it? Right? Like right now, I don't know everything here. This is the first time I've run a Cassandra 5 cluster. I'm literally doing this with you for the first time ever. I ran a one node environment to collect that test data in this Cassandra 15.4.52 that I told you about. But this is literally just me figuring out this stuff and including you all, because I don't know. I used to be kind of not into the idea of people seeing me not know things. It's like kind of scary, but now I don't care. I don't know anything. So let's see where this is at. Nice little share session right there. Okay, so see that? Great. Min threshold 4. So that's I believe that's T4. Node tool compaction stats. What are you going to do, node tool compaction stats? So how is everyone? Are you enjoying my 1 hour off the cuff rambling? Let's see now. Pinning tasks, easy cast stress, random access 1. I guess I actually haven't looked at the output and I haven't seen this formatted output yet. Easy cast stress, random access 1. So, all right. So random access has 1 compaction. Very. Yeah, buddy. Sarma, is there anything you want to know while I'm in here? If there is, just tee me up and I'll ramble for a while, man. Okay. What was I doing? Still seeing errors. That's cool. Let's take a flame graph. Let's see what's going on here. So I don't know what the system is actually doing right now. One of the things I noticed before, and let me just share something that I had. This is a flame graph from the cluster earlier. I pulled this up because I thought it was kind of cool. And then you are, this week I will start playing with easy cast stress. Yes. You're doing good. Thanks, buddy. I am learning. I have to watch this video multiple times to catch the many small things you're talking. Yeah, yeah, it's probably a lot. I know once I start going, I am like a freight train, and as you can see, I do not stop. The training won't quite be this intense. I'm not going to be moving this quickly in the training, and the training will actually be training is actually going to be a lot of hands-on. So when we're in the training program, it's actually going to be the students doing what I'm doing now. So this process that I'm mucking around and messing with things or running profile stuff, like this is a lot of what we're going to be doing in the class. Like we're going to be operating as a team, and we're going to be setting up these clusters and these environments, and you're going to be learning about how this stuff works and then applying the knowledge hands-on on clusters. Like literally everybody has root SSH access. I don't care. We're just doing it. And we're going to break stuff, and that's going to be okay because it's sandbox. So what we're going to do here is we're going to do a couple things. Start to use async. Yes, Thomas, async-profiler it's the best. It's literally it's helped me solve so many problems. It's helping me improve Cassandra, and it's helped me identify a ton of the underlying issues that I talk about all the time. And you know, I might if you've seen, you know, a lot of the talks I've done, then you'll probably be like, oh, John's talking about read ahead and compression again. Well, it's because it matters all the time. Like prior to 4.0, and most people are still unfortunately running 4.0. If you are, you should really be upgraded. 4.0 and especially 4.1, significantly better. Far, far more stable. Everybody I know that's using it in production has nothing but good things to say. People are actually talking about their on-call pager. People are getting paged less by upgrading. This is like, that's at the end of the day, that's what you want. And you should be able to run denser clusters, and you should be able to stream faster. There's actually zero copy streaming is in 4.0, and zero copy streaming streams entire SS tables. And the reason why this is so cool is because when we take a look at UCS doesn't get huge SS tables. So because you basically have a guarantee that your SS tables are going to, I believe there's a guarantee. I need to double check on this. I think that it always breaks on a token boundary. So basically what happens is when you add new nodes into the cluster, if you have an SS table and the node that's joining owns the entire range of data, Cassandra can stream over that SS table without going through the JVM, and that can be super fast. So maybe if we have time, if I get a look and I figure out what's going on here with the current cluster, I can I can take a look at what it would look like if we rebuild a node, and we can see what it looks like when we start looking at the data that's being streamed. That's actually why I did these settings, because got to be honest, I was really, really hoping that I'd have time for it. And for some reason, I love these 2-hour insane streams where I just don't stop talking and then go into a coma afterwards because I'm mentally exhausted. So let's take a look. AS Prof. ASPROF is the async profiler. So if you're using an older version, you would know that it was dot slash, it's either profile or profiler, tab completion. Now, when you set it up, which ASPROF, now, so now everything is packaged up a little bit better. So it's actually, so there. So you see that this is here, the user local async. So one of the reasons why I developed Easy Cast Lab is because I wanted an environment with all of the things that I like on it. And I'm super picky. If you can't tell, I'm very, very opinionated, and I want things, I'm like, I want it this way. This is what I need to test, and this is how I want it to work. And I'm happy to share that with everybody. But if you don't like the way it works, then it's one of those things where it's kind of tough because I'm solving my problems. I'm primarily solving my stuff. Anyway, so I have the, I love the async profiler. It's great. And I put it on this image by default. So some additional information, I'm going to be publishing. There's actually two images. There's a base AMI, and that one includes custom builds of some stuff. The reason why it includes custom builds of some stuff is because, well, one, BCC Tools, the one that's offered in Ubuntu via the package manager, I've been having a lot of problems with it in AWS. I don't know if if any of you have tried this, but if you install from the package, I'm finding that it's broken. So I install it here from source, and I use the latest build of it, and it's because it's got some of the newer tools, and it works better with the newer kernel because some of the internals of the kernels have changed. And so it's BCC Tools, FIO, and if you want to learn about FIO or BCC Tools for that matter, you should check out my previous streams. And there's some other stuff. Oh yeah, all the versions of Java, right? Like it's actually pretty cool how we have all the versions of Java on here. And then there's just one command called use Cassandra that switches between them, figures out the right version of Java that you need installed, and it like activates it, and then you're good to go. So this is literally a universal Cassandra AMI, and you can start a cluster in like 2 minutes. So anyway, let's take a look here. Am I still? Oh my God! Look at all these errors. It's erroring so much. I broke it. I broke it so bad. How did I do that? Look at that. It's broken, and we're only seeing 76% idle. So what's happening? So there's a couple things that we're going to take a look at now. And the reason why I love the async profiler is because it can really help you dig into problems really quickly. So we're going to take a look at, we're going to start with the CPU profile. So let's just do that now. As CPU.html. And then I have a, let's see if this works. I have a helper I have a helper tool on here called Cassandra PID. It just outputs the PID. So this should run us over here. So profiling 60 seconds. The other thing that we're going to do, we're also going to look at locks. So when you have something like, oops, a lab source unv.sh, there we go. Sometimes, not always, sometimes when you look at a system and it doesn't have high resource usage, but it's not behaving correctly, there's a few things that could be going on. One, you could be dealing with like a thread limitation. So it's possible, and let's take a look here at neutral TP stats. It's possible that we are just, we don't have enough threads, because I am doing, like, at one point this was doing 10,000 requests a second. Now it's slowing down, and we're seeing all these errors. Profile is done. No tool TP stats, not even loading. So sometimes what we find in these systems is that we sometimes are starved on threads. And you see here native transport requests. So we have 128 active and 309 pending. So that means that we're actually queuing at the transport level, which is kind of dumb because there's not really a good reason to do that. That is almost certainly the problem. So let's just go ahead and see what we can do about that. So I never remember the name of every config. There's too many. Let's just take a look here. So when I look at this number, I see 13 active mutations, 4 active reads, and all this is blocked, right? And then we see a ton of these guys, internal response stage blocked. So what's going on there? Wild stuff. So what we're going to do, and then hints, okay, so we've got some hints that have been dropped. Yep. Mutation response. All right. Yikes. So there's a couple things that could be going on here. This is still the observability phase. Like, remember, when I talk about the OODA loop, to me, this isn't something that like you just do for 5 seconds and then you go, oh, I have to rush to a conclusion. I think I know. Like, I still don't know what's going on here, and that's okay. It's honestly not that big of a deal. So let's do this. So we go to I can do there's a little inconsistency here, so I can type Cassandra 0 with SFTP. Cassandra 0, I'm just going to show you real quick how that works. There's something called there's an SSH config here. The SSH config here, when you provision the environment, it generates this SSH config, and then in the environment.sh file, it actually goes ahead and sets up all these aliases for you, and then sets up SSH-F to the local SSH config. So when you do this, you're actually getting SSH-F pointing to my the SSH config in this directory. So with C0, when you type in C0, it's actually an alias for SSH Cassandra 0. So this is how I'm able to basically like generate this environment that I can mess with as long as I have source.env.sh. What was I going to do here? So SFTP Cassandra 0. I'm going to go ahead and grab that. So look at all this. So ZGC so half of the time, I don't know if you see this. Okay. So this is kind of wild. Let's just go ahead and refresh. Okay. So half of the time here is actually spent with ZGC doing stuff. So that's interesting. That is really, really interesting. So there's 2 things here that are possibilities that should be looked at. One is the amount of stuff that's blocked in the native transport requests. I'm just going to go ahead and change that because I don't need to wait. That's, again, I know I keep saying it. That's why I built these tools. So here we can go into Easy Cast Lab, and let's actually jump into this environment. So we can see here, like, so clearly ZGC is doing a lot of work. That is actually crazy. It's crazy the amount of work. So this is like what's happening in order to not because it must be taking up CPU time, but we're not actually hitting high levels of CPU. So I think we still, I don't know. I think might still be limited on the configuration. So let's try. So if we go to, I'm just going to show you. So user local Cassandra current. Remember, that's the symlink. It always points to the current one. And then we go to conf. Okay. So let's just take a look at what we're going to want in here. Okay, so if we do this, start native transport true, that's great. You know what? I think, there we go. Native transport max threads. Okay. So we're just using that by default. Native. So let's just go ahead and see what happens when we increase this to 512. Probably a little bit reckless, but this is again the whole point. Quit. Okay, so exit out of here. You know, I talked a little bit about this, but I didn't show it, and this is pretty fun. So EasyCast Lab has, like I said before, a command called update config. Okay, you can just do UC in EasyCast Lab UC. Done. Okay, so here's why I like this, right? All I did was put this here, and I type in EasyCast Lab UC. EasyCast Lab goes in and takes the original Cassandra.yaml, patches it with this one, and puts it in place. So as it's doing this, let's just go over here. We'll take this out for a minute. If I go into user local, am I the wrong one? Oh, that is funny. I was on the stress box. Oh, I was on the stress box. This is, oh my God. I can't believe I was on the stress box the whole time. I didn't know it. Oh, that's why it was so confusing. Okay, let's bring this up here. Forgive me. All right, still not crazy. I don't know why it's so not doing anything. Okay, so it doesn't look like it's doing much. And then you can see that like these errors are still crazy and happening. So what we're going to do now is bounce each of these nodes. And I'm adding in, I don't have a rolling restart in yet, but what we're going to do is, yeah, thanks. Yeah. On that note, that is actually why right before I started this, where is it? So I have a, you know, all the work is here. Everything's public. I don't really hold stuff back. It's not how I roll. Right here, literally the last thing 2 hours ago, set host names and useful PS1. If I had done that, it would have been more obvious to me what was going on. But anyway, it doesn't matter. Boom. C0 sudo systemctl restart Cassandra. So I'm just going to go ahead and do this on each box. And it doesn't really matter. Which one am I on? Okay, I'm actually on the right box this time. Node tool status. And I should probably also, du so there's only 24 gigs of file of data here. Okay, so this one, let's see, has it. So go ahead and check TP stats again. And hopefully, hopefully this makes a little bit more sense, right? It's like, okay, if we were blocked before on the number of threads, maybe increasing the number of threads is good. Maybe it's not. I don't know. We're going to find out. It looks like maybe not. I have crushed this node. Let's see. So this is IOstat. Really useful for figuring out what's going on sometimes. But this node is like, check the logs. Ah, still starting. Okay, I just saw the thing scroll by. Cool. Replaying, blah, 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 blah. Neato. Replaying the commit log. Okay. Node tool status. Oops. Now at least it knows that it's not up. So I'm basically just going to wait for this, and then I'll go ahead and restart the other two nodes. Now, one thing that's going to be in here is there will be a rolling restart command, and you will be able to do like, so you did easy cast lab update. It's either upload or update config, and you're going to be able to do -- restart. I think I may have even already put something in there, but it won't do it safely. It literally just is like force restarts it. Yeah, restart. So if you set the -- restart or the -r flag, it'll just YOLO a restart. Down. It's fine. There we go. Okay, what's it doing? Hints? Why are you doing hints? Okay. Node tool TP stats. Okay, so now it's like, no, it's not doing anything. This should we should see some stuff in here in just a second here. It's possible that we're also not. I forget the exact order sometimes on like startup. So it's still doing hints. Are people able to connect? By people, I mean me. Let's see. Still 0. Bizarre. There is a new wait, I hope I didn't nuke my no. I think we have a something in here now for getting the client list. Okay, one anonymous connection. Nice. Let's just see what it is in the other nodes. So one thing that's kind of cool is you can do this, but this is kind of annoying. I'm not even sure this is going to work. 5.1. See what we get for client stats now on a node I haven't restarted yet. And then we'll go back in just a second to take a look at the other one and figure out what's going on there. Interesting. Why was the first node so much worse than the other nodes? That's weird. So normally in that type of environment, or in any environment, what you want is a good dashboard. I don't have my dashboards built into this. I actually have added support in here to work with the folks at AxonOps. They are basically sponsoring the training from the operational tooling perspective, because I don't want to build all the dashboards and repair and all that other stuff. I just don't feel like building a control plane. I just don't have time. So they are lending, they're basically giving us access to their control plane. And it's awesome because their control plane is really, really good. I've been working with them to help them, based on some of the work I've done, figure out like what the best way to render some graphs is, and kind of like, what do I want to see, basically, is what they've asked me. And so they've gone and implemented some stuff that I've asked for, and it's really, really cool. Unfortunately, they don't have support for Cassandra 5 yet, so I wasn't able to set up the agent, all that stuff. Okay, before I was looking at the client stats, I just wanted to see what that looks like over here. And then I'm going to go ahead and restart Cassandra on this node. Okay, see, there we go. That's what I'm expecting to see. Active, pending, 11,000 pending. Yikes. And we can see that our error rate is crazy right now. In fact, we're like only erroring. So look at this, 8,700 errors per second. We're actually getting more errors than we are anything else. So there's clearly something going on here that I need to investigate. This one, as a matter of fact, because this has so many things, I'm going to go ahead and grab a flame graph over here too. See, what was a C1? Lots of stuff is trying to run, and then let's use this Cassandra PID. What? Oh. Cassandra PID isn't on this machine. That was something I made that manually for the other node. Okay, so once I get this flame graph, I'll go ahead and take a look, and then I'm actually going to stop the workload. I want to take a look at the data on disk, because this is like throwing 7,000 errors a second. It's literally like everything is erroring. The problem right now is that there's this is nuts, right? Like there's just this huge basically blocked queue, so nothing can complete. It wouldn't surprise me if there was like a heap issue, but I don't know. So what we're going to do here is we're going to take a look at what's going on at the CPU time. And then I'm just going to grab this. This will be, so I'm at 90 minutes right now. I'm probably going to stop in half an hour. Oh, it hasn't done it yet. So I'm gonna actually switch back to the UCS side of things. So I'm going to switch the compaction strategy to the exact opposite of what it is now. So the strategy as it is now is set up for tiering, right? And so we're going to take a look at the way the data is laid out on disk. We're going to, okay, and I'm just going to stop this. This is no point. It's just beating a dead horse at this point, which you shouldn't do. Don't do it. Wow. Okay. We probably have a lot of stuff that was going on the heap for it to be doing this much. So this is kind of interesting to me. I'm definitely a little bit curious as to why this happened. Don't know. Let's just take a quick look. So I showed a bunch of stuff, right? Like I'm kind of bouncing all over the place. I'm trying to show you a little bit of everything here because the tools are interesting. Like UCS is interesting. Like the problem solving process is interesting. The fact that I broke everything is interesting, I guess. What was I going to do here? Oh, I think I was going to restart. And this is why you don't just start doing stuff in production. What are you doing here? So let's see. Mostly idle. So this should have everything in the queue should have expired by now. So this should be like doing nothing. Or if it's doing anything, it's probably doing compaction. Okay. Whoops. Oof. Yeah, so I'm definitely going to need to go in and figure out what is happening here because shouldn't have 8 million things in the queue and 4 things here. I don't like that. So the question is, did I forget probably an OS setting or something along those lines? Oh, we have compactions running. And back what we were here for. Back the whole reason I lured you here. Back to stats. Good times. So I don't know if this has been like the most valuable thing or the least valuable thing. Let me know. And that way I know to keep doing this sort of thing, or if this is kind of just one of those things where you're like, what is going on here? Then do something else. Okay. Yay. Look at these. We're doing it. We're doing it. This number, totally worthless. Average compaction remaining time. Don't trust it. Doesn't mean much. I actually had a Oops. Nice. Okay. So here's what's interesting here. Not seeing a lot of activity. Oops. Okay, so this right here, whoops. What I'm doing here, echo 2, and I tee that into proc sys VM drop caches. This is just a way of breaking the page cache, because I probably have a ton of stuff in the page cache. And then when we look back here, then we actually see things happening on NVMe. But not a lot. Oops. So I'm just going to do real quick, use a tool called CacheStat. CacheStat's really nice. 10 iterations. CacheStat 110. What it does is it takes a look at the statistics around your page cache, and it's going to tell us, boom, here it is. Hits, misses, dirties, ratio, hit ratio. It just tells us a lot of really interesting information. So, we're mostly hitting page cache here. Now, the thing that's really interesting is that even though we are, let me show you what I find quite interesting. We have, when I run no tool compaction stats, it was compacting, right? It said it was. But when we look at our disks, we're actually not seeing it do that much, right? And this actually comes back to what I was talking about before with the file system stuff. So we are going to do something wild here. Let's see how good my memory is. XFS slower. Let's do this. So we're going to do two things. One, we're going to profile. We're going to get the profile information, and we're going to let that run. Okay, cool. And then I'm on, which node is this? So this is the one that ends in 23.3, which is this guy right here. So Cassandra 1. Okay. So while this is running, and I'm gonna have to grab the profile output in a sec. We'll take a look at it. It's actually kind of cool here. So we don't have anything else going on except like a ton of stuff in the queue, which should hopefully be gone by now. We'll find out. It'd be really funny if oh, oops. One thing about this, this says could not open file. It's an error. When you run this, you have to put the file somewhere that the Cassandra user can put it. And the reason for that is because this uses something called JAttach, attaches the agent to the running JVM, it runs it, and then writes it out as the agent. So if you do this and try to write it somewhere as like root, it's like, no. Now, oh man. This happens sometimes. Profiler already started. I think there's a way to stop it, but I usually just reboot the JVM. What was I going to do? I think I was going to go back to my original thing, which was, oh no, I was going to look at XFS. So here's the question. Why is compaction not doing more IO? Like if we say go ahead and use 256 megs a second, and then like we're not getting anything here, that's not great. Like we should be, like if I do no tool compaction stats, I either expect no compactions to be running because there's like nothing going on here, or you know, if there still are, then it's like, why are we not getting good compaction throughput? Now there could be issues with the, again, this could just have like the heap just be completely full here because when we looked at TP stats, it's possible that there was just too much and the node is basically locked up and needs a reboot. Possible. And since if this thing doesn't recover on its own, right? If it hasn't recovered, I'll just go ahead and reboot this, and then we'll take a look at the system stuff. Yeah, so this still has 8 million things here in this internal response stage. Don't love that. So this is like, there's really not anything you can do here. Make a note of that for later. That's fun. See, I promised. I said I would break things, and I did. Let's just do system. So if you like breaking stuff, I'm your guy. Let's see. So this is also going to restart it with like the increased native transport. But there was something else going on there because this is bothering me a lot. The like it's one thing for I want to figure out what is going on here. Maybe a parameter that I can tweak here, but I don't know why it's not doing anything. Or it might not be doing anything because ZGC is just like no. At least that's the way it looked before. But hard to tell. Restart Cassandra. Cassandra's like, Okay, so I successfully broke Cassandra 5. First time using it. Destroyed it. I do it so you don't have to. Or I do it so that when I get a phone call, I know what to do. Yeah. Dropped. Mutations. 4 million. Yikes. Not doing well. Yikes. Okay. So now it's supposedly going. God, I have so much muscle memory. I'm like var log, mount log. Please talk 1 or 2 sentences about those drop mutations. Yeah, man. Sure. So drop mutations essentially happen when the when Cassandra is backlogged. It's a load shedding mechanism, and the idea is that it's better to like not try to process 8 million mutations or whatever is behind us. This is just it's a write. It's literally a write. So Cassandra was not keeping up with the writes for whatever reason. Like this is part of the process. And then there's a reason why this isn't released software, right? Like we're still working on this sort of thing. So, you know, internally, it can only do so much at a time. And so the question is, like, one, how do we make it go faster? Good question. And then two, what happens if we really can't keep up? So the best thing to do is to load shed in order to drop the mutations, and then they'll be sent in as hints later on. So it's not like the worst thing in the world. It's just like, well, I can't handle it. The problem is that this cluster, I've managed to completely overwhelm it. So all 3 nodes in this cluster are toast. Like they've been toast for a long time. It's actually why there was a discussion on the mailing list a few weeks ago, the dev mailing list. And the question is, should we have more like load shedding and rate limiting built into Cassandra? And personally, my opinion is that we should actually be adding this into the drivers. Okay, so load shedding, the best thing that you can do is to load shed as far upstream as possible. Because if I go all the way to Cassandra and then Cassandra has to drop the mutation, I still have to do the allocation, I still have to take the request, still have to do a whole bunch of stuff. If you can make it that the driver is rate limited, and if you make the rate limiter dynamic, similar, actually exactly like the rate limiter in easy cast stress that I did not use, what you can do is dynamically limit the rate based on metrics like the number of errors that you get back from the server. So back when this thing was erroring, right? Like this thing was erroring like crazy. A adaptive dynamic rate limiter would slow down. It would intentionally just be like, whoa, pump the brakes. It would tell whatever's upstream from it to pump the brakes. Okay, so this, let's see. This right here, if you're interested in this topic, let me just drop this in the channel here. So there's this library like that comes along with this post, and this is really smart. I didn't think of this. This was a I actually found out about this because I wanted to do a different type of rate limiting, and mine was going to have coordination between services, and I don't like that. Like I don't like that anymore because the coordination between services, like you have to know in advance what the rate limit should be, and this scales dynamically with like load on the system. So let's suppose that you have an upstream service, and then you have Cassandra, right? You have a 3-node Cassandra cluster. The upstream service is hammering Cassandra, and it detects that it's either over its SLO or there's errors coming back, whatever feedback mechanism you're using, and it starts to throttle itself. And then you go, oh no, that's not good. Let's scale up Cassandra. Awesome. What happens then is you double the size of your cluster. Well, now you can handle more traffic, right? You can handle double the throughput with the same latency. And the adaptive rate limiter, all of a sudden it goes, oh, I'm not getting any errors anymore. I can go a little faster. So it picks back up. So it's always, the reason why I love it is because you don't have to put in like configuration. You don't have to have someone there like pushing the button or making the adjustment or turning the knob or whatever it is. It just does it. It's really, really, really smart. And because it uses feedback mechanisms that are based on the metrics from the downstream service, you get to just let it go, and you never, it becomes easier because you can fail fast. So the reason why I love it so much is because if you're going to fail anyway, you might as well fail before you involve 10 other services in your failure. Like, you don't need to put all the pressure on the entirety of the system. You only just say, hey, like, end user, I was going to fail anyway. I'll fail now. And then I don't put any of the other pressure on. So it actually allows you to service more customers at a better experience, even though it seems really weird because you're just like, get out of here. No, I'm not going to help you out. Or I'm not going to deal with you. You actually end up with a better all-around system, because by load shedding a small number of your like end users, maybe you've got this like crazy peak traffic. Maybe you load shed 5%, but the alternative is like 100% of your service becomes unavailable. Like right now, in the state of like where my cluster was at, because I didn't have load shedding, I literally got into a point where Cassandra could not function. So if this was an actual operational cluster, 100% of my customers would be like, what's going on here, right? And I mean, and by that I mean, if they're whatever service I'm running for people, they wouldn't be able to access it. So 5% or 5% no, or 100% no. This allows for faster recovery. Adaptive rate limiting allows for faster recovery. It allows for a smoother experience for more people, and it is the best mechanism for handling massive increases in traffic and mitigating load. Last thing I'm going to do. Let's see if this is up. All right. So cool. Nothing's happening over here. Some stuff is dropped. Hint response dropped. Okay. No tool compactions outs. Oh, okay. It went ahead and finished all the compactions. That's okay. We're just going to come out of here. We're going to run. Now, the interesting thing about this is that the other nodes are probably dying still, but I don't care. Come back here, unified. Okay, so instead of this T8, let's just say like, let's just do something really dumb. Let's just go with like L20. Let's see what kind of pressure this puts on this thing. So what might happen is it might take effect on this node and not the others. If the other ones are, see that timeout. Probably should have increased the timeout for this, but whatever. Real rogue. Okay, good. Schema mismatch. Hey, this is a fun one. Schema version mismatch detected. I don't know. Drop a comment if you have seen this. This is definitely not a fun issue to fix. If you find this interesting, maybe I might talk about it. I don't know. It's actually, I would say that it's hard to set up, but I just set it up not on purpose. Let's see. Easy cast stress. Okay, see that L20 right there? Cool. So it's, at least it's here. Okay. So this should be going now. Okay, cool. So if I take a profile, oops. I'm gonna wrap it up after this. So this is going cool. Saw that before. I know how it gets there. It's very tricky to cleanly solve the problem. Schema version mismatch. Yes. So schema mismatch happens because Cassandra doesn't yet have a mechanism for maintaining consistent schema changes. So this is one of the things that like Accord, and if you've heard about Accord or transactional cluster metadata, this is kind of in that grouping of things. Consistent schema, I believe, is actually part of TCM, not Accord. But it's a whole consistent mechanism for maintaining state around the cluster. So instead of like everything being gossip and just like whatever, TCM is going to be a big deal that's going to solve a lot of problems with inconsistent cluster state between nodes. It's going to be really, really cool. So if you can't tell, I'm pumped. So let's just take a quick look. What did this look like? TCM targeted for 5.1. Yes. Yeah, originally we were gonna we wanted to have it as part of 5.0, but some more pragmatic people, I was against this at first, but it's definitely the right decision, decided or suggested that we push TCM and Accord out because it was kind of a question mark as to when it was going to be done. And so, you know, yeah, like a lot of people were excited for Accord and like a lot of people were talking about it. It was kind of like a huge talking point for 5.0. But 5.0 is going to be a huge, huge release regardless. If I manage to I may end up doing some more sessions here, but over time, I'm going to be doing some performance comparisons of 4.0 versus 5.0. I'll be doing testing zero copy streaming. Actually, I could test that now. You know what? I'm going to test it right now. Going rogue. Sure. Nope. Oh, I forgot an L. I was like, So we're gonna let this, we're gonna let it run rebuild right now. And then also I'm just gonna, I should have SSH on this node. Same node. Anyway, there's a lot of interesting stuff that's going into. Oh, looks like we're streaming. Fun. Okay, so this is going. Now, oops. Okay, looks like it's pretty quick. Oh, come on. They're really not. What's my networking? Oh, TCP top. Oops. Come on. You got this. Nice. Fun. Okay. So this is TCP top is a useful tool. It's part of BCC tools, as you can see here. I was able to, at one point, if I had been faster, there we go. So now I'm getting some information. So it looks like we're streaming in. Oh, okay. I'm gonna have to do some more tests. I'm gonna actually have to test this specifically because I'm really interested in getting some metrics around the overall performance here. But streaming in, I see it sometimes. It says that it looks like it's doing around 100 megs a second, but that's 100 megabytes, so it's actually streaming in pretty fast. So if I do probably a decent amount of compaction now, pending one. Okay, so compaction streaming are looking great. Maybe ZGC was the problem. So it might be. I might need to take another look and rerun some of the stuff with G1. I tried ZGC back with Java 14 like a while ago, or maybe it was Java 11 when 4.0 was out. I forget. But I didn't get great results out of it. So I don't know if this is an issue that stems from not having enough heap or it just not being ready, or it could be something else. Like I'm a little all over the place here. So according to this, there are times when we're actually writing 83 megs a second, and I configured this to do quite a little bit more than that. Again, this is why I like testing this stuff. Oh, look at all this. This is fun. Okay. So basically for future testing, gonna get in here, figure out like, was it ZGC? Was it the storage engine? Because remember, I also switched BTI. If we look at my list of things that I changed, And this is the reason why I like my patch file thing, because it's really easy to see what I changed. Concurrent reads and writes, don't think it was that. I didn't see anything that indicated it was that. BTI is something that was changed, and ZGC is something that was changed. So the question is, did I hit an issue that's a combination of those things put together? Did I just put too much load on the cluster? It doesn't look like it. Resource-wise, doesn't look like it. I think it should have been able to do more, and I need to figure out what's broken. There could also be like locks. So I'm just going to open this up real quick. So this is a flame graph I took earlier, and I was looking for, let's see. I was trying to find, oh, this is it. This is why I did it. So I have this, let me pull this up on some window. Okay, see this? So this is, actually you can't see it, of course. Oops. Oh man, what did I do? Okay. Okay, so look at this. I was running this before. Syscount -x. Syscount shows you counts of system calls. This is really cool if you're interested in figuring out like when you see like in MP-stat, where was it? Let me pull it up. And this is it. This is the last thing. And then I'm done. Okay, well, it's not even on a node. Come on. Not there. Okay. When you bring up MP-stat, there's this right here, sys. Okay. User, sys, IO8 is where most of your time goes. User is stuff like that's actually user level code. That's in the JVM. Okay. Sys is whenever you make a system call, you essentially are asking the kernel to do something for you. And there's a little bit of overhead. There's some context switching overhead. It's definitely slower than to make a file system call than it is to read data in from a buffer, for example. So the whole reason why I was actually checking this out before was because I wanted to see if we were having slow system calls, and I wanted to see if if that was affecting things. But what I actually found was that we have this futex call. So this is a semaphore. So that's actually I think that's what this is. So the question is, I wanted to get a stack trace around this and figure out where this was coming from, but I didn't have time. So I might do that after this. But I have been talking nonstop for over 2 hours now. I love doing this, but I definitely need to give my voice a break. So I'm going to wrap this up. Thank you very much for joining me today. This was, I hope, enjoyable. Whoa. Did I do it right? Yeah, there we are. I'm back. Okay. Thank you, everyone. I really appreciate it. If there's something that you're interested in learning about, leave a note in the comment. I don't know if this format is the best format for these types of things, but it's what I love doing. I actually really, 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 really enjoy benchmarking and messing with things and breaking things and seeing what I can find. I actually get a lot out of this. I'm learning a lot about what's broken, what's not, as I'm trying to show you stuff. Like, as you noticed, I grabbed a ton of flame graphs. These are all useful for me. I review this stuff later and I figure out like what's going on, and I use that to help me, get feedback to people or get, more familiar with code or functionality, or figure out what works and what doesn't work. And then I can also make recommendations because, I don't want to tell people to use something if it doesn't work. So right now, not sure what's wrong with, what exactly was going on. I don't know if I don't know if it's something I could have fixed, or if it's something internally, or if it's something in, I'm going to keep messing with it. But anyway, thanks very much for joining me. I had a really good time. I hope you did too. Definitely do the whole subscribe thing. And if you're interested in learning more and you want to become, if you want to learn these tools and you kind of want to go through this process, and you want to get better at running Cassandra in production, check out my training. It is going to be awesome. I mentioned Jordan West before. He's going to be joining me, and we're going to be teaching this thing together. So you've got two committers. Both of us have been operating Cassandra for, I've been doing it for over 10 years now. And Jordan is an absolute beast who's written a ton of internal code and has worked on some really, really amazing stuff, both at Netflix and Apple. So, I'm really excited to be offering this, and I hope you come join. And I'll drop a link in the description, and you can, hopefully check it out. All right, see you later.